Ladies and gentlemen, welcome to another edition of our Algebra 2 Flipped Classroom session. Little tougher theme song here today. I'll be very impressed to see if anybody nails this one. Hope you had a good Thanksgiving break. Hopefully you had lots of good food to eat, and now we're hungry for some new math here. Our title today is we're going to talk about exponential functions. We're going to focus on two main components. We're going to put a lot of energy into our graphing today, and then we're going to take a look at how we could apply our exponential functions to growth and decay models that we may see in the real world. The first one, we're going to jump right into an example today and try to grab one of those little sheets of graph paper that we hopefully handed out on Tuesday. But we want to talk about how we're going to graph the function y equals 2 to the x. The first thing, why is this an exponential function? Why is it not linear? Why is it not quadratic and all those things? Well, what you'll notice is, where is the variable? The variable is hiding up there in the exponent. So our first key is, because the variable is up there in the exponent, that's what makes it an exponential function in the first place. And I think it's important to recognize that. What we're going to do here is we're going to go ahead and construct a table of values, and feel free to employ your calculator here as a helping tool here. I'm going to plug in -2, -1, 0, 1, 2, and 3 for my x values if I can squeeze them in here. And certainly you're more than welcome to just go ahead and type this equation into your calculator. You'll probably, when you go to the calculator, you'll probably have to type in 2 and then the caret to get you up to the exponent, and then you can type in your x. But anyway, I'm just going to do this one by hand. If I substitute a -2 for x, I get 1/4. Let's see, if I substitute a -1, I'm going to get 1/2. See if I can squeeze it in here. 2 to the 0 power, just like anything else to the 0 power, is 1. 2 to the first is going to be 2. 2 to the second is going to be 4, and 2 to the third is going to be a very nice 8. So let's take a moment here to hit the pause button. Go ahead and plot these 6 points as carefully as you can, and then we'll come back and see if we get the same pictures. Okay, I've gone ahead and I've kind of imported two different pictures. One, the one up top here is a picture that I found. This one right here, this is a picture I just found on the website that I thought was very clean and clear and concise. And then down here, I went ahead and just did a screen grab on my calculator to show you what your calculator screen should look like. Now, actually, in both cases, you'll notice both of these graphs, you'll agree, go through the 6 points that we had over here in our table of values. But what neither one of these pictures really do is they don't accentuate what we call a horizontal asymptote. In other words, what I want you guys to put on your graph right now is a very straight dotted line right on top of the x-axis. I want this line to be very visible and bold, and I want it to stand out. And what we call this line is, we call it a horizontal asymptote. Okay, I'm going to abbreviate it here. Later on in the lesson, we'll actually spell the word asymptote all the way out in case you're wondering what it looks like. But basically what a horizontal asymptote is this imaginary boundary line that the graph continuously approaches without ever touching. So even down here in this region where it looks like the graph touches the x-axis, in fact, it does not. And if we had the capabilities here of zooming in several times over and over and over again, we would notice that there is a little bit of daylight between the graph and the x-axis. There's somewhat of a gap, and it never touches nor crosses that x-axis, and that's going to be a theme here today. So your calculator, even though your calculator does not show it, there is a horizontal asymptote down here on the x-axis that we're going to talk more and more about throughout the lesson. What I want to do here in our second slide is I just want to take a moment to compare these new exponential graphs to the old-fashioned linear graphs that you grew up doing in the the middle school and 9th grade and so forth. What we notice on this linear equation here is that our rate of change, okay, that's going to be a new buzzword we'll see more and more throughout our math career as we get into calculus and so forth. Our rate of change is what we call constant throughout the entire graph. Let's say whether I'm moving from point A to point B or from point B to point C, the rate of change between these points is constantly the same. But compare that over here to our exponential. Now we'll talk about rate of change, and we're going to say that our rate of change is increasing throughout the entire graph. If I move from point A here to point B here, not only did the graph increase, but it increased at an increasing rate. So we're just saying, and then again, you'll notice from B to C, again, not only is my graph increasing, but it's increasing in bigger chunks. So we would say that our rate of change is increasing as we move from left to right. The next thing I want to go over is just what we call some general characteristics of all exponential functions that are written in the form of y equals b raised to the x power, or f of x equals b to the x, where b is called my base. My b is whatever number quantity is being raised to the x power. And we're going to have a grand total, it looks like about 8 bullet points here we want to put in our notebook. And bullet number 1 states that all of these graphs are going to cross the y-axis at the same point, believe it or not, and that's the point 0, 1. Take a moment, look at the first graph we did, 2 to the x. I promise that graph crosses the y-axis at the point 0, 1. In fact, whether you're graphing y equals 2 to the x, or y equals 5 to the x, or even y equals 1/4 to the x power, all of these exponential graphs have that in common, that they're guaranteed to cross the y-axis there. And it's for a very simple reason. Any of these numbers, if you substitute a 0 in for these x's right here, any number raised to the 0 power equals, yes, hopefully you said 1. The next two bullets get grouped very nicely together. The first one says that if your base is a number bigger than 1, then our graph is going to increase, and that holds true for the one we just put in. When we graphed 2 to the x, our base was 2, that's greater than 1, and therefore we saw a picture that was increasing. And then vice versa, if our base is some number that falls within the interval 0 to 1, then our graph is going to be a decreasing exponential function. At some point we're going to graph 1/2 to the x power, and that's just going to kind of get reflected over the y-axis and be a decreasing function. Again, our next two bullets kind of go hand in hand together. The first one is our domain is going to be the set of all real numbers. Basically, that means it extends infinitely to the left and infinitely to the right in both directions horizontally. And then our range, we're going to talk about, how low does the graph go, how high does it go. Well, you'll notice the graph never dips below the x-axis. In fact, it never touches the x-axis. So we're going to say that the range is the set of all positive real numbers, and usually what we'll say there is that y is everything greater than 0. Can't equal 0, doesn't dip below 0, it's just everything greater than 0. Our next two comments go hand in hand. We're going to say that all of these exponential functions, they pass the vertical line test. No matter where you put that vertical line, they'll never intersect more than once. Therefore, that means the graph is indeed a function. And then again, it does pass the horizontal line test. No matter where we draw this horizontal line, it'll never intersect the graph more than once. Therefore, it's not only a function, but it's a very special one-to-one function. So there we just snuck in a little review on a topic here that we covered back in September. A one-to-one function passes not only the vertical, but also the horizontal line test. And we saved the last, or the best for last here. We're going to talk, this is the one I get most excited about. We're saying that the graph is asymptotic to the x-axis. And all that means is that somewhere here on the graph, like the one we drew earlier, that looked like this end of the graph is progressively getting closer and closer to the x-axis without touching it nor crossing it. And that's what asymptotic means. Okay, we're going to look at a couple of equations and try to decide whether we would classify them as an increasing or decreasing function without actually graphing them. Of course, you usually do have the freedom to throw them in your calculator on a test just to be safe. In this particular function here, it's an exponential function because my variable's in the exponent. I've identified my base as having a value of 1/2, and because that number falls somewhere between 0 and 1, I'm going to describe this as a decreasing exponential function. Second one, let's see, again, a pretty friendly one. If we set f of x equals 8 raised to the x, I've identified our base as being 8. 8 certainly greater than 1, therefore we'll describe this one as an increasing function. And then we save the best for last again. A little bear trap hiding here in this one. Let's say 3 raised to the negative x. Now the temptation here is to instantly say, well, b equals 3 and therefore it's an increasing function. But what we've got to do is we've got to rewrite this. So we're going to reciprocate the base, which then changes the signs of my exponent, sign of my exponent. we always want to make sure that the exponent's positive before we decide what the base's value is. So now I can say that the base has a value of 1/3, and because that falls in the interval 0 to 1, we would classify this as a decreasing function. So just a little bear trap there on that third one. All right, we're gonna roll up our sleeves and try to graph a very challenging exponential function here. Let's try y equals 3 raised to the x plus 1 power minus 2. So there's lots of challenges here. The first thing is it's not exactly as easy to type into the calculator as you may think here, but we're going to try to generate a table of values starting with -3, and we're going to go all the way down to +2. So let's see here. We got 0, 1, and 2. And I want you to go ahead, hit that pause button. See if you can type this equation into your y equals menu, and then go to your table and fill in the table of values. If we get any really absurd decimals, we'll go through decimal places and call that close enough for our graph today. Okay, hopefully you got the same numbers that I have here in orange. Notice that the first couple we put down in our table were rather ugly. If we didn't quite get the same values, let's go back and take a look at your y equals menu and see if you typed in and entered your equation the same as I did. So here's what my calculator screen looked like. Now my calculator is the updated version, okay? Now whether you have the updated version or not, the key here is I want you to really focus on that having parentheses around your exponent right here. This parenthesis here and this parenthesis here are extremely crucial. And then of course the calculator demands that we use a minus sign as opposed to a negative sign. That's another common mistake that sometimes we accidentally use the negative sign there. So hopefully you had good luck. Hopefully you got the same numbers over here that I got in my table. Now we're ready to go grab our graph paper and plot these as carefully as we can. Keep in mind that they're also asking me to eventually write the equation of the horizontal asymptote. So I want to challenge you as you're graphing these points to try to guess where that asymptote is. So now that we've plotted all those points as carefully as we can, hopefully your image looks something like what I've got here on my calculator screen. It looks like the graph lives mostly up in the first quadrant and then down kitty corner in the third quadrant where it starts to flatten out a little bit. But the ultimate question is, where is this asymptote hiding? We can kind of eyeball it here on our graph. You know, it looks like the graph is approaching some invisible boundary line right here, where it's getting closer and closer to that imaginary horizontal line without ever touching it. But the ultimate question is, what is the equation of this line? Now, all horizontal lines start off in this format: y equals some random number. You know, is it y equals -1? Is it y equals -2? Is it y equals -3? Or somewhere in between there with decimals? Well, one option here is you could go back to your table of values on your calculator and start to scroll up that table. Okay, and you'll notice as I go higher and higher on that table, the y values are getting closer and closer to -2. In fact, they get so close to -2 that the calculator just kind of waves the white flag, gives up, and just says, hey, it's -2. Technically, it's not -2. Technically, it's still -1.9999999 with several nines there, but eventually the calculator just rounded it up. So what you're starting to hopefully suggest here is that y equals -2 is the equation of that horizontal line right there. In a nutshell, the way that you can always tell is you go back and you look at your equation, and whatever that last term is right here, that number will tell you exactly where the horizontal asymptote got shifted. Whether it got subtracted or added, that'll always tell you the equation of the asymptote right there. So far we've talked about very basic, simple exponential functions, and now we're going to start to use them to model some growth and decay formulas and functions that we see happening in the real world, whether it's the population growth or decay of a booming or shrinking town, maybe it's the growth of a bacteria culture or whatnot. The list goes on and on. Basically, the big difference is we're going to now add a coefficient in front of our b to the x term. It's very important here to realize, though, that only, okay, and this is a huge asterisk right here in our notebook, only the b is being raised to the x power, okay? The a is not included in that exponent. That's going to be a huge difference maker today. As we try to describe some of the letters here in this crazy function, and sometimes I just like to rewrite it as y equals a times b to the x. The letter a represents the initial amount. That'll make more sense as we dive into some examples. B represents either our growth or sometimes our decay factor. Okay. X represents time, whether it be 2 days, 2 hours, 2 minutes, or 2 seconds. X will represent the amount of time that has elapsed, and then Y represents the ending amount. Again, a lot of these terms, though, they may sound rather confusing right now, but hopefully once after we do an example or two, they'll start to reveal themselves and make more sense. I want to get a little bit more specific about what that B term represents. Besides just calling it a growth or decay factor. If B happens to be greater than 1, then what we have is a growth we're modeling a growth situation. And then if we do B minus 1, that will tell us the percentage or the rate at which the population is growing. That's a very common question where they want to know the percent. The flip side of that is if B happens to be some number between 0 and 1, we now have a decaying model. And this time we're going to do 1 minus B to get the percentage of decay, or the rate at which a certain population or culture is decreasing or decaying. Okay, we're going to take a look at two models that either describe a growth scenario or a decaying scenario that we may see in the real world. Our first one is related to growth, and it just describes the population of the popular town of Smithville in the year 2003, and they say that the population was estimated to be about 35,000 people that year, with an annual rate of increase or growth of 2.4%. Now, as far as that growth factor, we described the growth factor is the B value that we see in our exponential function, and so we need to try to solve for B. We also had just in that last slide, we mentioned that B minus 1 is always going to equal the percentage of growth. And so what I'm going to do is I'm going to substitute the 2.4% in for the percent growth, and I'm going to basically try to solve this for B. First things, we're going to go back to middle school here and just convert this percentage into a decimal, where we slide that decimal place 2 places to the left, and then we'll add the 1 over, so my B value is 1.024, and we're going to describe that as our growth factor for the town of Smithville. The next thing we want to try to tackle is writing an equation that will model future growth. We said y equals a times b raised to the x power is our generic formula. We just found our b value back here in part A. We just need to talk about A. We described or defined A as the initial amount, or in this case, the initial population. If we were to assume that 2003 is the beginning of the problem, in other words, x equals 0 or t equals 0 at that moment, then our initial population is right there at 35,000. So we're going to say y equals 35,000 and then 1.024 raised to the x. I really like the use of parentheses here in this problem. It just emphasizes the fact that only the b value here, 1.024, is being raised to the x power, not the 35,000. Now the last thing we're going to do is we're going to try to use our equation that we just wrote to try to determine or predict the population in the year 2007. Now, what we want to be really careful of here is back earlier we defined 2003 as x equals 0, or the beginning of time for this problem. So 2007 is 4 years later. So we're going to say that 2007 means that my x value is a 4. And I'm going to simply substitute that 4 into my equation. Just showing my substitution here, like many of the other problems we've done this year, is a very crucial step. It's your way of communicating to the grader, where your thoughts are at. And then I'm just going to go ahead and I'm going to grab my calculator and I'm going to type all of this in one bang. And we'll see what we get. Pay attention, be very careful with your rounding, and we'll see if we agree with the same answer. This is actually a very tricky rounding problem. The first thing, when I plugged into my calculator, I had 38,481.91 people. Now the trick is they're not asking for the nearest hundredth. you'll notice there's no TH at the end of 100. So they're not looking for two decimal places. What they're actually looking for is for the hundredths place, which is right over here where the 4 is. And we just want to decide, do I want to round down to 38,400 or round up to 38,500? I'm going to go with 500 just because of the fact that that 8 is bigger than 5, which is then going to push my hundreds up to 5 itself. So there it is. There's my predicted population, and I thought the rounding was very tricky on that one. Okay, down the home stretch we come. Here's our last problem for the night. We're going to try to cruise through a depreciation, also known as a decaying problem. Two words that are synonymous with each other. The first thing they want me to try to tackle is to identify the decay factor. Again, that's another name for my B value. Could be the growth factor or the decay factor. For decaying type problems, we said that 1 minus B was equal to the percentage of decay or depreciation. So we could say 1 minus B has to equal 15%. Middle school, we learned that 15% is equivalent to 0.15. If I try to solve for B, I'm going to end up with 0.85. So there is my decay factor. The next thing we're going to try to do is now we're going to try to write the equation to model this decay. We're going to start with the same generic formula. Let's see, we already found our B value, and our new car started with a value of 25,000. So there's my initial amount. I'm going to substitute that in. That's my A value, so I'm just substituting straight in for A. My B value is 0.85. We're going to close that in parentheses and raise it to the x power. That's my equation to model this decay. And then last but not least, they want me to try to predict or estimate what the car will be worth in 10 years. So we're going to substitute that 10. We're going to substitute the 10 in for x and try to solve. So we've got y equals 25,000 times the 0.85 being raised to the 10th power. We'll grab our calculator. We'll try to type in that entire piece at one time and see what we get. What we'll do here in this case, anytime we're talking about money and they didn't specifically tell me where to round, we'll just go to the nearest cent. Seems like the most common sense thing to do. I ended up with $4,921.86 would be the predicted value of his vehicle 10 years from now if it depreciates at a rate of 15% each year. So there it is. Lots of little things to memorize, such as, 1 minus B equals the percentage of decay and so forth. Lots of little formulas, but we're going to lean heavily on our notebook tomorrow as we work through the homework. And then hopefully by the time we get through that homework assignment in class, there'll be a little more intuitive and it'll just kind of come naturally to us. So good luck, and we'll see you tomorrow.